All right, recording is rolling. Welcome to Thursday. Got an outside lab today. You guys remember these spring launchers? They're back. And today I'm going to have you guys figure out what is the spring constant of the spring. And here. Now, maybe one direct way you could figure that out is by directly applying Hooke's law. You guys remember what Hooke's law is? F equals kx. So if you could figure out the compression force and how much it compresses, you could just do F equals kx and you could get it that way. But we're not going to do that way. I'm going to have you guys use conservation of energy. So something to do with 1/2 kx squared. You guys remember, I don't know if you remember, I told you guys that there are sort of like two categories of labs that we do in this class, like different approaches, like ways of thinking. Like one category is we pretend that we're cavemen and we don't know how physics works or what the equations are, and we're going to figure out those equations. Maybe we have somehow have equipment like stopwatches, but otherwise we don't know. And the other approach is that you know all the equations, you know all the relationships among variables, and that you're trying to solve for something specific. Right? This is that category lab, the latter category, where you're allowed to know 1/2 kx squared, you're allowed to know conservation of energy, you're allowed to know kinetic and potential energy formulas. You're trying to figure out what is the spring constant. Okay, so how are we going to do that? Okay. So I'll help you guys out a bit. This could actually be a really good FRQ type question. So for experimental design, they might say determine spring constant and do something with conservation of energy. Okay. Now these aren't the only two ways to do it, but these are probably the two most straightforward ways. Right, so one way is you could put the launcher on top of a ledge, on top of the balcony. We're going to have a balcony in a few minutes. Right, aim it straight horizontal, and if you know this balcony height and this distance, you could eventually ascertain what is the spring constant. Another setup you could do is you just put it on the ground, aim it straight up, see what is the maximum height it goes to, and that can also to the right. Now, I'll help you guys out with a few things. One is, do you guys think that the gravity field is going to matter? The gravity field going to matter? Like, how about this? What if you took this whole system to the moon and you found like some small cliff that was same height as the balcony out there, and you shot this off the moon? Do you think this distance would be the same on the moon? Would it be smaller? Would it be larger? Yeah, it would definitely be bigger on the moon. So does gravity field matter? Yes, it does. And the way that AP says it, they have some phrase that they always use. It's something like and any fundamental constants that may apply. And you're like, aha, I know little g is like about 10 meters per second squared, right? Or 9.8 if you want to use 9.8 meters per second squared. Right. And then a similar story over here. What if you did this setup on the moon? What do you think this h would be compared to Earth? Yeah, it would be a lot. It would go a lot higher on the moon, wouldn't it? Right. How about the mass of the ball? I mean, mass has canceled out quite a bit in the last week or two, right? So, do you think that the mass of this ball is going to matter, or do you think it's going to cancel out? Right. Oh, yeah. Oh, okay. How about let's do a sort of quick thought experiment. What if you loaded a marble inside this launcher, and then you went back and you reran the experiment with a bowling ball? You just load a bowling ball in there, somehow fits in there. Do you think those are going to land at the same distance? No. Which one's going to go further? It's got to be the marble. That makes sense, right? Or what if you did this setup? Which one do you think would blast higher, the marble or the bowling ball? Again, definitely the marble. Tell you what, anytime a spring is involved, mass does not cancel out. Now, if you're just going from gravitational potential to kinetic, like the Tarzan problem or the Galileo dropping stuff off the tower problem, in that case, mass does cancel out. But whenever a spring is involved, mass does matter. You guys just told me that would be the case, and you're right. Right, so I'm going to have you guys write up a procedure and get to a conclusion of what is K. We're going to do this a little bit different. You guys know I usually give you that format of like what's the question, what are the measuring tools, right? And then procedure is like how do you go about gathering the data, and analysis, like how do you either apply graphs or equations to get the answer. Let's just push those two in one section, the procedure and analysis, because it might be convenient to say like measure this and then do this calculation, like say for a time of fall, okay, and then do this procedure and get this number, and then do this calculation. If it's more helpful, then that's okay. I'm not going to worry so much about that. Okay. Then I get a conclusion at the end. Of course, spring constant is so many. What is the unit for spring constant? What's the unit? What per what? How do you measure stiffness of a spring? Ooh, you guys remember? Okay, how about this? Let's look at the Hooke's Law version of it. This is Hooke's Law, which you guys aren't going to use today, but you could use this to figure out what's the units for K. Because what's the units for force? Newtons. What's the units for compression? Meters. So what does K have to be? Newtons per meter, right? Is that the only thing it would, right? Okay. So you're going to get some spring constant in newtons per meter. Okay. Now, before we head out there, I'll tell you guys a couple of tidbits. The mass of this ball is pretty much, speaking of this ball, okay, there's a really important experimental detail I have to tell you guys about. Right? These are different balls than before. Right? And I told you guys to do before is to put the ball in and then ramrod it in. And that's what I told you guys to do before. Don't do that this time because this bouncy ball will get jammed in there and it's really hard to get out. Okay? So here's what you guys are going to do instead. Use the ramrod first. Go click, 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 like so many clicks. And after, right, after you ramrod it, then put the ball in. Okay, so see if you guys are following. What are you going to do first? Are you going to put the ball in first, or are you going to ramrod it first? What do you guys say? Yeah, you're going to ramrod first. Okay, otherwise, you guys are going to have a fun day of trying to pick a ball out of. And speaking of the ball, everybody's ball is about the same mass. I measured this ahead of time, so I'll go ahead and give you guys this number. This ball, the mass is about 6.4 grams. Some are a tiny bit less, some are a tiny bit more, but they're all about that. So you just use that number, this experiment will work out fine. Guys, when you're doing your calculations, do you want to use the number 6.4 for the mass? No. Why? Has to be in kilograms. How many kilograms is that equivalent to? Yeah. Decimal rolls back 3 places, right? Okay. Kilo, factor of 1,000. Okay. And I'll give you guys one more number that'll be useful, which is the compression. Right, so you guys remember how this launcher has like three compression settings? Okay. So say you do 1 click, okay, and then stop that here. If you do 2 clicks, let's assume it's scaled linearly, so it's like twice the compression distance. Twice the compression distance. What ratio did the energy stored in the spring increase by? And it's not a factor of 2, it's a factor of 4, because 1/2 kx squared is the energy stored in the spring, right? Okay. What about 3 clicks? So 3 times 1 click. So 1 click to 3 clicks. How many times the energy stored in the spring? 9 times, wouldn't it be? Right. And what is that distance? Okay. So that's the last number I'm going to give you guys. Okay. So here's the way you can do this. Okay. Just to save you guys a step out there. Okay. Is you can set this ramrod in there. Take this pencil, make a mark right here. Okay. Then push it all the way. 1, 2, 3 clicks. I'll just give you guys the 3 click number. If you want to do 1 or 2 clicks, then you can do this yourself. Okay. All right, that takes us to like this Velcro right here. Okay. Pull this out. So what's the difference between my pencil mark and that? That mark and where the pencil's now. I'm looking at 7. Okay. It's 7.3 centimeters. Okay, 7.3 centimeters. Okay. So if you use 3 clicks, then the compression distance, maybe I'll call it x to be consistent with this, right? Okay, would be 7.3 centimeters. Now, when you plug in compression distance in your calculations, because you guys can use maybe like energy stored in a spring is 1/2 kx squared, right? For x, are you going to plug in 7.3? No, you're going to plug in what number? 0.073, because that would be meters, right? So you guys know centi, like 100 cents in the dollar, so you just roll back this decimal 2 places. Okay, you guys know that? Okay. You guys good so far? All right. The other things we guys out here. Right. So these 2 setups, the one on the left is through kinetic energy, and I'll tell you guys why. Okay. So all these energy conservation setups, you always go from some initial point to some final point. okay, and then say what are the energy types. And you might be tempted to say, well, initial point could be in the cannon or inside the launcher. Maybe the final point is when it's hitting the ground. Could you solve it that way? Yes, but that would be an incredibly complex problem that takes lots and lots of paper. Okay. The more straightforward way is to do this. This kinetic energy here turns it to 100%. Sorry, this potential spring potential energy here turns it to 100% kinetic energy right when it's left the cannon. Is that right? If you could somehow figure out the speed, right, think how you might do that. Then you could say this 1/2 kx squared equals this 1/2 mv squared, and you could eventually solve it like that. Okay? But then it's the puzzle of like how do you get the speed? Okay? But there's a way. It might have something to do with this distance. Might have something to do with this volume, might do. Okay? The other way you can do it, if you aim it straight up, well, I said this is via potential energy. Now remember, there's two kinds of potential energy. There's spring potential and there's gravitational potential, but it's just gonna go from one to the other, from here to here. Okay? That's going from the launcher 1/2 kx squared to 100% mgh, right? And then if you could grab that height, you could work and get paid that way. Is that good? Okay. And last detail before we head out is that I have a stack. You guys see this stack of papers and sleeves right here? Okay. Let me show you what that is. So since we have limited class time, the idea of like what AP wants to do, like the philosophy of this class, is that I'm supposed to not say anything more to you guys. We head out there, you guys figure out spring content. I've sort of given you guys too much stuff already. Okay. But because we have limited time and whatnot, here's a cheat sheet of how you could get to the answer for either one. So see if you can come up with this on your own, as you're writing on your own paper. You guys put your name on your paper. You're going to write out the full procedure and analysis and get the conclusion. Okay. But you may want to glance at this from time to time and just make sure you're on track. Okay. You guys good? All right, let's head out.